Okay, good afternoon, everyone. So I'm Andrea Bartolini from University of Bologna, and I'm today here for presenting our work on empowering OpenPOWER in terms of energy awareness. So the outline of my presentation will start with presenting the D.A.V.I.D.E system, which is a supercomputer based on OpenPOWER system and Pascal GPU installed in Cineca in Italy, which has been designed together with D.A.V.I.D.E engineering. And so we present, introduce D.A.V.I.D.E. Then I will give some word on why it's important to have fine-grained monitoring in future HPC systems and why are the key use cases for that. And then I will describe the key innovations that we developed together with D.A.V.I.D.E. So first, a few words. So we are on the organization that has founded the design of the D.A.V.I.D.E supercomputer, so PRAISE, which is the organization which is formed by all the different the member country of European Union and aggregate all the different data centers in Europe. And as you can see here in the map, we have the different countries which are involved in the PRAISE consortium. And in small in the center, you can barely see, we have the two partners, so E4 Engineering and University of Bologna and Cineca. So there we have a small area in Italy, in the northern center of Italy, in which we have a lot of competences in supercomputing centers. We have a data center, a PRAISE data center, tier 0 data center. We have a university such as us, which does research on this topic, and we have E4 Engineering, which is a system integrator of computing systems. So the D.A.V.I.D.E system is where D.A.V.I.D.E stands for developed of an added value infrastructure design in Europe. It's a supercomputing center. It's 3 clusters, 45 nodes of Power 8 plus NVLink and 4 GPU per node. I will go more in depth later on. And it's been ranked on July and November in the top 500 Green 500 list. So the target of this design, and this was the mission that we got in designing the system, was to improve the way in which energy efficiency is perceived and how it can be handled and controlled in future supercomputers. Up to date is the only OpenPOWER system in the top 500 list. So the computing node of D.A.V.I.D.E is an OCP form factor. It is based on the IBM Minsky computer design. It has two IBM Power 8 plus NVLink. It has a 4 NVIDIA Tesla P100 card, and it takes power from a bus bar, and it has liquid cooling on top. The liquid cooling has been designed by Azatec, which has been partner of the design, and has been actually the cooling support for the Power 8 has been designed within the project. And then in addition to what you have in the system, we have, as a University of Bologna, we have designed a fine-grained power and performance support, monitoring support, integrated within the computing nodes. So we have added, and this is where the arrow points, we have added an additional component which is in charge of handling the out-of-band monitoring of the system. So the target use case and the scenario that we have for which we have designed this component in the system is the following. So the target use case that D.A.V.I.D.E tried to solve is the following. So on the left side, we have a sketch in which we have the different compute nodes of the system. We have a compute node of the system. We have all the several components. We have CPU, accelerators, card. We have other hardware components such as the DRAMs. And we have also some mechanical components such as the rotating fans, which are used to cool down the system. Then we have in the design we have 2 users, so the red and the blue, which are normal user and allow user to access the system. And then we have instead the malicious user, the one on the top, which tries to have an attack on the system. And at the same time, you have that some parts in your system may have some degradation and reliability faults. And these are also, which is also light by the other arrow. So in today's system that uses coarse-grained power monitoring of the consumption, what what you have is that you cannot really see a lot from the power trains in sense of what is happening. You usually can see the power at the speed of seconds, and this doesn't give you enough speed for understanding what was happening. So with fine-grained power measurement, what we target is the fact of actually having a resolution on the way in which we monitor the power consumption of each of the node, which is fine enough to see the different usage of the machine. So to highlight the part of the workload that are on the red user, the one for the blue, and also the parts which are spikes, which are related to the malicious user or to a fault which is happening on the machine. So fine-grained power and performance measurement can really help in verify and classify node power performance, understand if something's in spec or out of spec, and also enable predictive maintenance on the node and be capable of accounting for user consumption. On the right part of the plot, what we have is instead this other scenario in which we have a system power capping. So basically for several reasons, which are related to the fact that you may have a new installation on your system, so you need to compress the power, to reduce the power consumption of the system that you are running, or you may have that you have some service level agreement with the power grid, so you have some requirements that can allow you to be feasible in terms of the power consumption, or you may have that you have some power shortage, or you have some natural disaster that decrease the amount of power that can be fed in your computer, in your machine. So what you want to do is basically being capable of controlling the maximum power profile of your machine and keeping them in a shape which may vary in the system during the time. And you want to do them in a way that doesn't compromise too much the performance and the way in which users use your machine, so in the way in which you account the usage of the machine. So the main, so in order to do that, we developed together with D.A.V.I.D.E 3 key innovation technologies. So here I sketch basically the computing nodes of the system and some additional component which I'm going to dig in, and also I'm going to end the front end of the system which is running, executing some additional software components that we have designed together with D.A.V.I.D.E. So the first component is what we call the black box system. So we have added the board that I was showing you before. It's basically a black box which comes together with your node. It's based on open hardware and open software installation, and it's basically capable of always seeing the power and performance of your system without completely being out of band. So we leverage what the OpenPOWER system gave us in terms of the capability of being capable of monitoring the performance and of all of the components which are inside, and some detailed power consumption of internal components from out of band, so without running any additional software in the system, so being completely transparent to the user and without stealing any computing cycle to the system. Then we added to this an accurate and fine-grained capability on the power measurement, so we can actually measure the power of each of the node really with a fine granularity, and we'll see later what this can lead to. And then we use, for handling the data, we use an Internet of Things communication. We use MQTT, the protocol that allow to push out the values with a really low overhead in terms of the packet which transmit which are traveling. And also this also supports time synchronization protocol, so you can really have a timestamp which is associated with each of the point of your measurement and be capable of correlating with what is happening inside the node. Here's just a snapshot of what we can measure with D.A.V.I.D.E. So the first with this additional component. So you can really see you start from an application for several minutes of a computation of a benchmark, and then if you zoom in, so the question is, can you really see things at really fine granularity in terms of the power? So if you look, the first zoom in is about a zoom of a 4-second time. We can see that there is a lot of activity which is going on the power. So we are actually measuring at every millisecond here. So we are pushing out at every millisecond for each of the node, the power consumption of the node. And we can see actually that there is a lot of activity which is ongoing. And we can also see here on the bottom plot in which we have for all the node, the power consumption in just one second window. And you can see all the time in which the GPUs are active. You see the spikes in power, so you see also a huge variation in the power. So it makes sense to see power at this granularity, and you can really appreciate changes. So this was the first question. But okay, then second question, can we really correlate this power measurement at 1 millisecond scale with what's happening in the application? So we ran on D.A.V.I.D.E some tests. So here I'm showing you in application, we wrote an MPI application, which was basically getting a timestamp and then starting an execution in all of the node of the system, in 8 of the node of the system. We take this timestamp at when all the application was starting the running, and we took the measurement from the additional board that we added to monitor the power. And what we can see actually is that we really get the point. So the timestamp is really getting the point which we see the power changes. And I let you see that the plot which I'm showing here is the power measured at 20 microsecond granularity. So we really have a synchronization because thanks to a good configuration of NTP and also the PTP protocol that we have in the system, we can really have sub-microsecond error on the timing of the timestamps, and we can really synchronize what we see on the power trace with what we see in the application at microsecond scale. So that's, I think, is really impressive in the sense that we can really correlate really fine granularity traces on the power measurement. And if you think of, and this is happening all out of band, so there is nothing which runs within the core. If you think at other systems which use a way of exchanging communication through the operating system to the application in order to see what's happening in terms of power, you are bounded by the operating system refresh rate, and you barely can go, it's hard to go below the millisecond scale. Here we are at 20 microsecond. So it's and really super accurate timing. Then, okay, but what do we do with this fine-grained granularity? Here, turns out that in the board that we are using for measuring the power is also capable of doing some additional computation. So if you remember our primary goal, that was the one of be capable of identifying some good application with respect to some attacker on the system. So here are two applications, an application attacker, and this is an FFT, which is done online on the power traces computed at 20 microseconds. So each of the nodes are capable of doing a spectrum analysis of the power consumption. It's kind of having an oscilloscope always on and connected to each of the nodes, which can tell you what's going on. And you can see that actually different frequency spikes, so different spectrum are related to different behavior of the application. So you can really be capable of recognizing one application with respect to another. So if you have a normal utilization of your system and you profile it, you can correlate it with other applications which are not in terms of spectrum with what you thought it was good. And then you can apply machine learning technique on top of that to recognize good usage and bad usage. Okay, but can you do it, this kind of analysis on this large machine in real time? So this is the second technology that we created in D.A.V.I.D.E, so, which was the one of actually using big data technologies and artificial intelligence technologies for handle the data that we produce in monitors. So we produce more than 1,000 metrics, 1,400 metrics per node per second on each node. And then we have all to handle them in order to create correlation in between what we sense in terms of power and performance and what the system is doing. So we used, in a login node, we have a tool chain which is actually capable of receiving all the data which are coming, creating a structured way the information, then create some view which are helpful. So we call this system, it's called Hexamon, which is actually the framework that we use for collecting the data. So I was saying I was saying before, on the first layer we have the daemon, which runs on the embedded system, which publish the data as soon as it monitors with the timestamp. Then we have an MQTT broker. Then we have an abstraction, which is Kairos DB, that gives you an abstraction for creating time traces on the data that you collect. And then you have a Cassandra database in which you can store the data scalably. And then you can also, so if you add the monitor node, if you increase them, you can increase the node that use the amount of resources for handling the data. And then with this one, you can have then a structured view for your information from which you can actually correlate the data and give different view. So how the things works in reality? So we have that each of the embedded system is reading the data and is publishing them to a centralized entity, which is the broker, which receives the data, and then it's propagating them to an IP, to an entity which actually receives this information and store them in multiple nodes in a Cassandra database. Then all these data are timestamp associated, and then you can correlate with other timestamps that you have in your application. On top of that, you can also apply some machine learning techniques, so you can have Spark, PyTorch, and other things that you can use for to have AI on top of the data that you are collecting for your system. So somehow you want to apply AI technology to the management of your nodes in order to understand what's happening and simplify the life of the system administrator and for the users. And so you can also, with this approach, you can also have some micro-batching approaches in which you actually in stream generate models and do some analytics on the data that you collect from all the nodes. And then you say, we have Spark, and we have Spark in which we can actually create the data, create events, and then are stored in the database again. So, but okay, now we have everything in a database, what we do. So we create two different visualizations for data that we monitor. I will try also to give you a live demo of a few seconds if it works. So just here. Okay, so we have first view, which is Grafana, but I need to, of course, move it here. You didn't view it. So these actually are all the metrics that we collect for all the nodes. So we have actually here several, this is a node of D.A.V.I.D.E, now live, which is actually doing some computation. And you can see that out of band, so we monitor a lot of metrics which are interesting. So it's the node 45 of the system. We have the GPU power consumption live in time. We have the PMI, the power consumption of the fan. We have there. Let me just also need to move the mouse here. Okay. Then we have a lot of other metrics. So we can create. If you want to know how your node is consuming in terms of power, without this out-of-band monitoring, you can actually know that now you have this balancing of the power within your node. Then you have also other interesting metrics, such as you want to know how the utilization of the different cores when running the benchmark is done, how the frequency of all of the cores is executing in real time. You want to know also maybe how is the throughput of your system or the memory bandwidth that you are using lively on each node. And this happens even if you don't have to call a profiler for seeing this information. So it's always-on information that you collect 24 hours a day, 7 days a week. And we always get this data. In order to, of course, this data would explode if you store them always. So what we do is we actually keep a buffer of 2 days or 3 days of this data. And then naturally, these are actually expiring it. And in time, we actually create an aggregated value of this data, which are for job. And this comes the second tool that we have created and this is Hexamon Web. So actually, this is a web portal for the data. So you basically just we also have implemented, of course, the job scheduler. So you actually, after your job is executed, you just have your Slurm job ID. You place in the tool, and then you can actually view all the data that we have collected. So you can actually get the node utilization, where your application was running, the gigaflops, how the frequency was actually executing. This is good if you actually want to some nasty things which happens with the power management of your system, so they may create some performance changes in your system. Then you can also know if you are good in terms of power management. So if you are actually, when you are idle, if you are really reducing the power consumption of the node, then you have also a live profiling of what is your memory usage. So, and this is super useful because as a user may actually attend off the job, a user may have not selected to profile his job, but he may have some doubt that something was not running as expected. So by using this tool, you actually have, since you have an always-on profiler for your application, which doesn't cost anything because it goes, everything is out of band. So it doesn't really cost nothing. So it's in the system. And you can always have analysis which run on your system. And so coming back to the presentation, so this was the view that I was showing you before. So we have also a view in which you actually can see lively how the different location of your system are in terms of power, temperatures, and other information. You can also see as I was saying, how much power has consumed your job and things like that. Then we have on top of visualization of the data, okay. But then this means that the user should be in front of the data trace. But can we apply some machine learning technique to this data in order to have some automated way of handling the data? So this is done actually, so the third technology is actually the one that we wanted, is to add the capability to the system to work at a fixed power budget. So you can select the power consumption of the node and work at this fixed power budget. So how we did it? Basically, we had a technology in which we don't want to change the way in which the compute hours are actually charged and accounted to the user. So if you have a user, at least in the site in Europe, the user is charged for computing hour. So if you are under power cap and you change the power consumption of the node, the user may see a performance degradation. But then how much the user should pay when you have decreased the performance of the system. So what we do here is actually a smart filter. So we create a predictor based on the information that we collect from the job. We create a predictor that is capable of telling you how much power consumption is gonna consume a given job before the execution, based on the user request and the user node. And then what we do is basically we use as an additional resource the power consumption, and we let only the job that fits with power consumption budget to enter in the system. And this actually is how it's sketched there. So you don't want actually to have more nodes, more power consumption than what is your power cap. And this actually, but you can also combine this with other mechanisms which actually control the power. So you can, predict the power consumption is going to be 10 kilowatt, and then I give a budget in hardware of 10 kilowatt to those nodes. So you are also safe in terms of that this power will not exceed your power budget. But can we really predict the power consumption of the node before their execution? So here are some plot that we got with our monitoring of different jobs which are executing in the system, and you can see that is actually, you can get a 5 to 10% of accuracy in the job prediction before the execution. So a final word about D.A.V.I.D.E. So it's really efficient. Actually, it turns out that it is efficient. So at the beginning of our project, we had an energy efficiency, average energy efficiency of a Green 500 system of 3.2 gigaflops over watt. And the agency that funded the project asked us to have a 30% per generation of computer. We should have been more efficient than this 30% of generation. So in the first implementation of D.A.V.I.D.E., so when we tested the first time without the OCP and without the liquid cooling, we're around at 7.7 gigaflop per watt, which was better than the threshold that we were in spec. Then finally, after we configured, so thanks to the liquid cooling and also to the OCP form factor, we reach 9.3 gigaflops per watt. And we can see that the liquid cooling is really working because we have below the 1.5% of power consumption on the fans. And this is actually a snapshot of the power consumption during the impact of each of the nodes computed with our monitoring system. So in conclusion, yes, with D.A.V.I.D.E. we actually show that we can create systems which are turnkey in terms of monitoring of what they are doing, and we leverage a lot of technologies that are key technology in OpenPOWER system. And the technology that we have developed on D.A.V.I.D.E. can be applied to any data center. So do you want to see it on your next P9 and Volta system? So we are here. You can come to talk with us. And here is some acknowledgement of the team which has worked on the project. So from University of Bologna for computing engineering, also Wistron, and also acknowledge IBM for the support and also NVIDIA for the support. Okay. Thank you. Sorry, can you say it? Yes, it's a 5 to 10% prediction, but this was actually, so we did it on a previous, so the question is, can we really predict consumption, and how is it working, the power capping? I guess the question is about. So the prediction is as an error, so I say between 5 to 10%. So we didn't actually run, this is a good test, we could run actually against the same job with different datasets to see how the things change. So we give, as a predictor, we give a lot of information. So we give the users, we give all the text that is inside the running script. So somehow we have also a way of learning something additional with just the pure components. But on top of that, you have also the fact that as you have, at end you are interested in capping the total power of your system, it's also true that all the errors somehow average themselves. So even if you commit some statistical error on one job, then at the end of the day, you are going to also have some other jobs which are statistically going to compensate that part. And as I was saying, this technique, we made some research in last year that can be really combined with per node level power capping. So if you use the prediction together to the capability of be sure of enforcing that power capping in the best way, so using some hardware technology for supporting the hardware power cap, you can basically combine the benefit of the two. So the prediction gives you a good hint on the total power of that job, and then you ensure that you don't overpass this limit by using the hardware mechanism. And this also will basically tell you that you are minimizing the impact on the execution time of your job. So the two can be combined together. And this has shown that work well when you combine the two together.
So what's the kind of the costing model environment that is driving the power-aware scheduling and the optimization of the computer for power? Like what's the computing center environment that causes it to be more cost-effective to run the computer potentially to schedule jobs based on power instead of maximizing the use of the acquisition cost?
Okay, so here I would say two words to answer this question. So the question is, which one is the cost model which stays behind the fact of controlling the power consumption for a data center with respect of actually maximizing the throughput always? So there are different scenarios. So the first goal of D.A.V.I.D.E was not only controlling the power, it was creating power awareness. So, which means that until you don't have an always-on and fine granularity system that tells you the true power of your system, you don't know really how you spend your power. So the first thing is that be energy aware somehow and power aware means to be capable of understanding how you spend each joule of your workload. This is the first goal. And the cost model is just to understanding. When you have a good understanding, so then you have different techniques that you can do which are power aware. So a technique will be a technique that is not against the fact of running your system at the maximum performance always. It's the fact of minimizing the energy of your application, but when you are under power cap. So even if you think you are not power capped, all of your nodes are power capped, because then the scaling is end. So basically, you could go faster, in theory, of the performance that you can really, of what you get, because you are power limited at the node level. Each CPU is power limited. So in that sort of, if you enter in that domain, so whatever you can save in terms of efficiency can give you higher throughput. So you can even show that you can go faster if you are energy efficient in some circumstances. But this is not the case. Then you have instead the case of the total power consumption of your system. And this actually is sometimes in something that is needed by external causes. So you may have a natural disaster. So for 1 month, you cannot have the power consumption to power on your system. So it's something that you need to have in terms of being safe. So even under that circumstances, you want to be capable of operating your system at the maximum efficient with this new power cap. So in that sense, it's not something that increases the efficiency, your cost efficiency, but allow you to be capable of running your system under a natural disaster case. This happens in Japan, for instance. And you may also have that then you have also this, you have other cases in which actually you are not truly feasible in terms of power consumption. So you may, when you design your data center, okay, you know that your average utilization of your system is not 100%, is not a lean pack run, but it's going to be the 70% or 80%. So you may want to design your power supply for your system to that 80% and the cooling to this 80%. But in cases that you have so that you need to have somehow a way to ensure that you will never overpass this one, because you are not designed for it. Then you have, so these are actually, I would say, the first goal. So per se is not a tool that you will not, so there are some theory that also, you can also think about over-provisioning your system, but it really depends. So it depends on the turnaround of your system. So if you really throw away your system after 3 years, your costs are really dominated by the hardware. So you want to use it at the maximum and have the maximum science out of it. But you have external code in which this technology want them to have it. And then, of course, as I was saying before, having the awareness of how the power consumption happens in the really fine granularity, you may discover that you can save a lot when you are in different phases of your application, and you can see that. In that sense, it's going to go to speed up your application under a power limit of a single node. Okay.